Okay. Okay. So, can I not look at myself? Please. Thank you. Go away. No, I don't want to see myself. Go away. Okay. You just go over there. Okay. So, here's homework 1. That text size okay? Can everyone read that? Okay. So, homework 1, this was just a really quick introduction to how to write basic R code and how to use R Markdown. So we're actually using 2 different programming languages. We're using R and we're using Markdown. So Markdown is like a really simplified version of HTML, right? That makes documents look really nice. It's really, if you go on Wikipedia and you click edit on anything, you'll see that Wikipedia is entirely written in Markdown, really similar to what we're using here. So Markdown is a kind of document presentation language, a kind of web publishing language that you'll see all over the place. But what we've done with what our studio has done is folded R and Markdown together to create this fancy thing called R Markdown, which can do both Markdown and R at the same time. So you're actually learning 2 programming languages. I'm sorry, but I promise it's worth it. Okay, so this is obviously just a demo, right? But remember, in our studio, in our Markdown, if we want something to run in our document, it must go in a chunk, right? And so this right here is a code chunk. Lasers don't work on screens. Oh, wait. Lasers don't work unless I do that. Okay. They still don't work on screens. Okay. So we have the triple tick, which is the top left of your keyboard. Curly brace R, which tells our Markdown that we're going to be writing code. The curly brace tells it, I'm writing code here. And the R tells it, I'm giving you R code, right? So I'm saying, here is code, and it's in R. And everything between this triple tick and this triple tick will be executed, right? As if it were in an R script, right? So all of that would have been in your document's output. Now, right, obviously reading is reading. Loading in libraries, right? Once we have them installed, we didn't have any challenges with loading in any libraries. Everyone was able to install Yeah.
Well, the only thing I didn't know this, but like when you try to convert it, when you try and like knit it into an HTML file, if you have installed, when I had install packages on there, it wouldn't let me. I had to delete that out.
Correct. You don't want to run install packages in your script because then it's going to install it every single time you compile the document. But we only need to install it one time on your computer. So the best way to install a package is to just go over to your console right here and just run it on the command line once. And then it's installed on your computer forever, right? Until you delete it. But that will persist across multiple sessions, so we don't need to install. So when we're running something in R Markdown or in an R script, we're going to use a library and not install packages. Library loads it in and makes it available for us to use. Okay, I know some folks had challenges with this one. Now we're going to create a new variable in Gapminder after we've loaded Gapminder in called pop1000. And the way we do that, one way to do that, there's a lot of ways to do it. But one way to do it is to use the $sign notation. So Gapminder is a data table, a data frame, or a tibble. They're interchangeable in a lot of cases. So what we're going to do on our data frame Gapminder, we're going to create a new column called pop1000, and we can name it and create it at the same time. So we're going to say Gapminder $pop1000. That's something new, so we're going to make an assignment to that. And Gapminder pop1000 is going to be equal to something that already exists, Gapminder pop divided by the constant 1000. So what's that going to do? It's going to do that, but in like mathy terms. What's it going to do? It's going to divide a vector by a constant, right? So we have pop here. It's going to take Gapminder pop, which is this, like 1,700 numbers, right? It's this vector of all the population figures for every country year in the data. So I call it a country year because we have a country by year. So our level of observation for this data set, each row represents a country in a year, right? So I call it, this is a time series data set. I'll call it country year level observation. So for each country year, we have a population estimate, and that's what this is. It's for the entire data set. Let's see how many we have. I'm going to use in row to figure out how many observations are in there. 1,704. So we have 1,704 population numbers. We divided every single one of them by 1,000 with this line of code. Right? So we did 1,700 operations with one line of code. That's efficient. That's cool. Okay. Next, I want to compute the mean of life expectancy. Any questions about this one? We're going to cover more ways to do this today. Questions about creating a new variable? Questions about calling a column in a data frame? Dividing by a constant? Feel okay about that? Okay. Next, we're going to compute the mean. And again, we're going to call Gapminder life expectancy. I can just highlight bunches of little slices of code and hit Command Enter to run only that, which I have highlighted. And so in this case, this is the vector Gapminder life expectancy. This is 1,700 values for life expectancy for each country year in the data. What I want to do for this is I want to take this vector of 1,700 numbers and compute a mean for that vector. What does it mean? It's a simple average, right? So it's the sum of all the values in the vector divided by how many observations are in the vector, divided by the length of the vector. So in this case, our length is 1,704, and we put that in the denominator, 1,704, sum in the numerator, that's our mean, right? It's the average life expectancy across the data set, and it's 59.47. But that returns a single value. When we did this operation, we returned 1,700 values, right? The same length as the original vector, but computing mean returned only one value. So we have some operations that are going to summarize over a vector, and some operations that are going to do a vector-wide operation that will return a vector, right? Cool. Unique. I'm just kind of getting us to experiment with some of the functions in R. Okay, so unique is going to tell us all of the unique values in country. Now note, when we looked at Gapminder, the first 6 rows that we see in the head are all Afghanistan, right? But when I look at unique Gapminder $country, I only get Afghanistan one time. What unique does is it returns only those values that are uniquely not duplicated in the data, right? So it's going to only provide Afghanistan for me one time, Albania for me one time, no matter how many times it appears in the data. If I want to know how many times each one appears in the data, I can use the table function. And now I can see that for most of these countries, I have 12 observations, right? 12 observations for Afghanistan, 12 for Albania, 12 for Algeria. Some of them have fewer than 12. I think generally for countries that didn't exist prior to 1957 in the state they do now. Okay, questions about unique, really similar to mean, but it's also going to return a vector. This time, the vector, though, is 142 long instead of 1,700 long, right? The length has gone down because there are duplicate values in country, right? Afghanistan appears multiple times. Albania appears multiple times, but my vector of unique names of countries is going to remove those duplicates. Yeah? Okay, cool. Unique is a function that is so handy and you will use a lot. Okay. Now, here I just wanted you to copy and paste the code from Healy's chapter on producing a scatter plot, but check it out. Oh, gotta load my libraries. Okay. If you ever see this error in ggplot, could not find ggplot, that tells me I have not loaded the package ggplot, which is part of Tidyverse. So that error message tells me I haven't loaded my Tidyverse package yet. And so I went back and I loaded my Tidyverse package. You're going to run into errors in R. R is not the best at telling you what you did wrong, right? Because it doesn't know what you were trying to do. all I can tell you is I don't know what ggplot means. And so after a while, you're going to figure out what these errors mean. In this case, I know that that means I haven't loaded my package yet. I need to go back and do that. But check it out. With 4 lines of code, we can make a pretty attractive scatter plot, right? That's a nice looking scatter plot. ggplot is what we're going to use for data visualization in this class. And it is an incredibly powerful and flexible data visualization tool that makes publication ready graphics. All of my papers use ggplot to make the graphics. So that's a pretty nice graph. Oh, that has logs, sorry. Here's the first one. Okay, so here's the first plot that we were looking at. Someone asked about making it a little prettier with labels and titles, and that's great. So we could use the labs function. All I do is put a plus at the end. For ggplot, if I want to string together multiple commands, I just put a plus to add new functions onto the end. Let's say I want to put x equals GDP per capita. Instead of the variable name, I want to make it more descriptive, right? And life exp, that doesn't look great. Let's make it y equals life expectancy. You're gonna see me do this where I try and put one argument on each line. And that's just to make my code more legible. It doesn't change how the code will run, but it makes it more readable. So every time I hit a comma and give a new argument, I'm gonna hit enter to put it on a new line, just to keep my code readable. Then we could do title equals scatter plot of life expectancy by GDP per capita, countries 1957 to, I don't know, 2019 or whenever this data set ends. Then if we want to get fancy, we could do subtitle equals, how cool is this? And there's more we could do. Labs has a lot of arguments we can pass to it to make different labels. But that's a label function. And so there's my new plot now. And if I want to get a better look at that, I can click zoom to see what it would look like in a higher resolution. That's not especially good because of zoom. But, right, so that's a nice looking plot. We can get silly and we could do, I just want to, yeah, I'll get a little absurd for a moment. Where are you? We could also, so we started to play with the aesthetics here, and we're going to do more of this next week as we'll do a more deep dive into ggplot next week. But we can get silly here if we want, and we can add additional aesthetic arguments. AES stands for aesthetics. So what am I taking from the data and mapping onto some visual element of my plot? So here, let's say maybe I want to make color equal to continent. Now I've made each dot in the graph correspond to the continent that the country's in, right? That's a column in the data frame. So ggplot has assigned the pink dot to Africa, the yellow dot to the Americas, the green dot to Asia, the blue dot to Europe, and the purple dot to Oceania. It's a little hard to see, but that's, we can keep tweaking this. If I wanted to present this, I might then increase the transparency on those points so we can see in between them and kind of get a better sense of where points are on top of each other. Right, lots of ways we can improve this, and we'll get there. You don't have to know all this yet, but these are just kind of like, I'm showing you how flexible this is, right? I can do whatever I want to with this once I learn how it works. I didn't expect you to do any of that, though. Okay, what I expected you to do was copy Healy's code and do that. Oh, another thing I like to do, so the indentation is a little off for me here. If you hit Command I after selecting a block of code, it'll indent it to line it up to where you can see that it knows where parentheses close. You can see here that I have this highlighted and it shows me this parentheses is closed. So it's going to come down here and say, this is attached to ggplot, but it's not part of this AES. And it's going to keep it all lined up so I can tell which function I'm working in. Command I indents. Yeah, it redoes the indentation, or Control I on a PC. Okay, so let's look at this plot and interpret it for a second. We're going to spend a ton of time looking at dots on grids and interpreting them in this class. So what do we see? Anyone want to offer me a quick interpretation of what we see going on here? Let's hear from someone else for a second. I'm going to do like an informal, like, I want everyone to talk, but like, if you've just talked, sit on your hand until like 1 or 2 other people have talked. What do we see going on here?
Pretty strong correlation between the two variables.
What do you mean when you say correlation?
As one, there's an association between how one goes and the other one goes that's consistent throughout.
Right. So when we say correlation, we imagine we effectively imagine a line passing through these points. And in this case, we can imagine that line looking something maybe like this, right? So that means that we see a positive association between GDP per capita and life expectancy. Can someone interpret what a positive association means in this context? What does it mean to say that there's a positive association between GDP and life expectancy? Right. So for higher values, and that is the sort of classic way we interpret it. As GDP goes up, life expectancy goes up. That's a causal kind of framework, right? That's saying if I increase GDP, life expectancy will go up. I'm going to like encourage us to use a more descriptive way to think about it rather than a causal way to think about it. So I'll say for higher levels of GDP, we tend to see higher levels of life expectancy. So we're not, it's a really subtle difference, but that way of speaking doesn't say that GDP is causing life expectancy. It just says when we observe high GDP, we tend to observe high life expectancy, right? And if that subtle distinction sounds crazy to you right now, that's fine. I'll explain to you through the course of the semester why that's an important distinction to make. But higher GDP, higher life expectancy, yeah? But you do see a pretty clear curve going on here, right? What can someone tell me about this curve? Is the relationship between GDP and life expectancy consistent for all values of GDP? Go ahead.
No, plateau.
Yeah, plateaus. Yeah. Yeah. There's a vertical, yeah, there's definitely a vertical asymptote at the x-axis at 0 because GDP can't be low, can't be negative, right? And life expectancy also can't be negative. But we do have a vertical asymptote here. And we also see that there's a pretty clear plateauing of the relationship as it increases. And this is a classic logarithmic curve, right? Which says that the expected increase of life expectancy for a 1 unit increase in GDP is super high when we're close to 0. But it actually gets really low when we get far away from 0. That is, for a country with a 60,000 GDP per capita and a 90,000 GDP per capita, this graph isn't showing us much of a difference in life expectancy. That's a 30,000 GDP difference. But between 0 and 30,000, right, we see a tremendous difference in expected life expectancy. Whatever. We see a huge jump in life expectancy moving from here to here. And we see basically no change from here to here, right? And that's what, that's a classic logarithmic relationship. And I'm going to apply a log to GDP per capita, a natural log. And we're going to look at it again. And we can see once I've done that, we can observe that we are now looking at basically a linear relationship, right? So I would say that the relationship between GDP per capita and life expectancy is log linear, meaning that after we log transform GDP, the relationship is linear, which suggests, right, that what a logarithm is going to do is it's going to compress extreme values down quite a lot. So that gap between 30 and 60,000 now is a gap between, 8 and 12. And so we can see more movement over that range because we've squeezed in those extreme values. We basically pulled in all those extreme values with the logarithm function. Because remember, exponents grow and grow and grow, and a logarithm undoes that, right? A logarithm is the inverse of the exponential. So it's going to pull in those extreme values And when we look at it on this scale, the relationship looks basically linear. So the curve is still there in the real data, but now we can see that on the logarithmic scale, it does appear that there's still a relationship here. It's just that it's working exponentially. Yeah.
So the only difference between, so like, 'cause I guess I was having a hard time with that homework.
I didn't expect you to explain that to me perfectly. You will not be penalized if you did not say this is a log linear relationship.
Okay. But it's like the log, like where we apply the logarithm, that takes out the extreme values and it just gives us a better representation of what the relationship is.
That's right. It doesn't take them out. What it does is it says, okay, so see this dot here on the extreme end?
Yeah.
That's the highest value for GDP per capita in the data set, right? So that's pretty close in to the bulk of the observations now. But look what happens over here. That same point is over here when we don't log transform it. So what it does is it basically pulls these ends and pushes this down a bit, right? And it basically takes those extreme values, pulls them in, takes those smaller values and spreads them out, right? And so we can see a little bit more of what might be happening as an exponential process, right, of growth. And here we can see it pretty clearly, but sometimes we can't, right? And so we'll get into the math of why we do this later. I just wanted you to see that you can put a function inside your aesthetic call and that it will change the plot. That's what I wanted you to do, is to see that I can use a logarithm on my X here and it'll change the way my plot works. That's what I was after. Was not after the math, was just after, hey, let's play with ggplot a little bit, right? Okay, so these solutions are going to go up now. Sorry, I'm just going to push them up to GitHub and the slides for today as well. This is, for those of you who are like, what the hell are you doing? This is just my terminal. I'm just telling my computer to work with Git right now to push these up to the web. So now if you go, oh wait, admit it. Now, if you give it about a minute and you go to the website, the slides for today and the homework solutions will be posted. Okay, so questions about any of that? Homework grading is going to be relatively lenient. I'm not looking for perfection. I'm looking for effort, right? So where you will get knocked is if you submit homework that's incomplete, that's clear that you didn't put a lot of time into it. Where you will not get knocked is if I'm seeing that you really thought about something, you put effort into it, you tried to solve the problem, maybe you made a mistake. That's okay. But the sort of the challenge for me is not receiving work or receiving incomplete work, right? Incomplete work is better than no work. But my grading is more akin to a pass-fail than it is to a like A, B, C when it comes to this stuff. And we're graduate students. I don't know if people have told you this yet, but in grad school, it's basically an A or not an A, right? So grading is not that important to me. It's important to me that you put the work in. Okay, GPAs don't really matter anymore, except if you're a master's student applying to a PhD school, and then they kind of matter, but like, whatever. I'm not gonna go too far down that rabbit hole. We can talk about all the dynamics of graduate school grading at another point if you would like. Okay, so, whoa. Oh, I was just sharing my desktop, and that's what I want to do. Okay. Well, let's go to the slides for today. I'm not going to do homework reviews every time, but when I think something's particularly challenging and new, I'll go over them in class. And the solutions will be posted most of the time the day the homework's due. I may hold the solutions if I have a lot of people who haven't submitted yet by that day. Okay, today is going to be all R code. And I know the readings on the syllabus have directed you to read a bit. And again, the readings suggested, not required, but we'll be covering the causality material from the EMI book. If you have been reading it, we'll be covering that next week. And we'll be catching up to all that material, but I felt like we really needed to get a good handle on R before we push through. Okay, so let's do a kind of further deep dive into data analysis in R. Problems, we already covered that. Here's R. Again, R's calculator. We already knew this. We covered some of this stuff last time. But let's kind of refresh ourselves really quickly. Right, addition, 5 plus 3. Multiplication, asterisk is multiplication. The slash is division. The caret is the exponent. We can do comparison operations. 5 is greater than 3. Yes. R will return true when a statement evaluates to true and false when a statement evaluates to false. You can also use T and F as short for true and false in your code if you want to do that. 5 is less than or equal to 3. So that's our less than and equal sign. Right? We just put an equal after it. 5, when we want to do a direct comparison of equality, we need to use 2 equals, because remember, a single equal in R is an assignment operator. So to do a comparison operator where we ask R, is 5 equal to 3? We need 2 equal signs. Is A equal to A? Yes, in quotes. That tells R that I'm not pointing to an object called A. I'm pointing to the character A. So if I wrap something in quotation marks in R, I'm treating it as a character, a symbol, not as an object. If it doesn't have quotes, it's going to be treated as an object, meaning I could have stored something called A that's equal to 3, right? Now here's storing 2 into A as an object rather than as a character, right? So now what is A equal to? A is equal to 2. A plus 1 is going to be 3 now, right? B is A plus 2. So what is B going to be equal to? What is that? 5? Well, you want to say 5, but I never overwrote A. I just asked R to evaluate A plus 1. So A is still going to be equal to 2. And in this case, B is going to be 2 plus 2. So B here will evaluate to 4. Even though I told it A plus 1 and it said 3, that's only happening in the environment. It's not overwriting the object A unless I explicitly reassign something to A. Right? And in this case, what is A going to be equal to after these 2 lines of code? So A is 2, 3, right? So we'll overwrite 2 with A plus 1. 2 plus 1 will now be 3. And if I were to run this again, A is A plus 1, it would then be 3 plus 1, 4. And then 4 plus 1, 5. I could keep running this line of code over and over again to create a counter if I wanted to do that. Right. Our objects can take a lot of different types. And one way we can evaluate the type of an object is with the class function. So in this case, we have what we'll call an atomic object, right? It's not a vector, it's not a matrix, it's not a data frame, it's just a single number. We'll take the class of it, and R will tell us it's a numeric object. If I make B equal to howdy, and I ask R what is the class of B, it'll tell me it's a character. And it knows that because I've wrapped it in quotes. If I tell R that C is equal to true, and I ask for the class of C, it will tell me that's a logical. So there's a logical type in R that can take on the values of true or false. If I put capital T here instead of full true, it would also register as a logical. Or capital F would register as a logical. I could spell out the word in all caps true, or the word in all caps false, or capital T or capital F. Those will register as true and false logicals. R is case sensitive, right? So you have to be careful with that. Okay, we talked about this last time, but it doesn't hurt to review again. Yeah.
What about like true but with lowercase r u e?
Yeah, so let's see what happens. You can always experiment.
It's got to be all caps.
It does. Object true not found. So it's saying, I don't know what true is. But if I tell it that, capital T RUE has special meaning. That has the meaning of the true value in a logical, right? But if I also do C is equal to capital T, now it's going to return true as well, because it knows capital T stands in for true. If I do is true equal to false? No. Is true equal to true? Yes. Is false equal to false? Yes. Cool. I typically use just the capital T and F, but while you're starting, it might be helpful for you to just write it out so you know what you're doing. Right. Cool. So logicals are really helpful. We'll kind of see a lot of use cases for those as we go. Vectors are one-dimensional arrays of values of any single class. Vectors cannot be mixtures of classes. A vector has to be a single class. So what type is vector 1? What class is vector 1? Numeric. What class is vector 2? This is a character vector, right? We have 3 characters. R doesn't care how long they are. It treats them all a single letter. It could be a whole freaking book I could write in one value, and it would still be treated as a single character object, right? It could be 14 words, doesn't matter, or a single letter, or just a blank space. If it's wrapped in quotes, it's a character. And R is going to store that verbatim as a character. So here's vector 2. We have 3 elements, A, fancy, vector. Right? So if I were to call vector 2 bracket 2, what would I get? I would get fancy. Okay, vector 3, what class is this? It's logical. Okay, and now we can do vectorized operations. We saw this with our pop column conversion in the homework, but I can take my vector 1 and I can multiply it by a constant, right? So 2 times vector 1 is going to multiply each element of the vector by 2. So 2 times vector 1 returns 4, 6, 8, 10, 12. 3 times vector 2 would do the same thing. We can also use a comparison across a vector. So we have vector 3, true, false, false. Is vector 3 equal to false? And then it will ask that operation over every single element of the vector. So no, it's not false. Yes, it is false. No, it's not false. Yes, it is false. Yes, it is false. Right? Is this making sense? So we can take a single operation and do it over the entire vector. Yeah. The concatenate function is the easiest way to do it. If you're just manually defining a vector, turns out you're not going to do it that often, except for when you're teaching vectors. Because in practice, you're working with data that already is in a vector format. But yeah, if you want to create a new vector, use the C function and list each element of it separated by commas. So the C function here is concatenate, and it's saying concatenate just means stick together. Stick true, false, false together. That's what this says. Make a vector out of it. Okay, functions, again, we covered a bit last week, but R has boatloads of them. We could think of these as verbs, right, in the language. R has tons of these functions. In practice, you know, as you get started, maybe learning 10 to 20 of them will be all you need to get started. As you get more advanced, you might build up to 50 to 100 of them. And you know, there are more, but oftentimes they're doing slightly different versions of the same thing. So functions run a fixed set of operations on some arguments. Functions return a value that can be assigned to an object. Functions take the general form of function name, parentheses, arguments. Right? So we pass something to a function and it returns something back to us. Right? We give it an input, it gives us an output. So here's some common functions in R for vectors. Maximum, max is a useful one. So it'll ask what's the largest value in that vector? 6. Min is the minimum. What's the minimum value of that vector? 2. Right? What's the length of the vector? 5. What does length do? How many objects are in the vector, right? How long is it? Okay, what's the mean of the vector? We used this one already, but it'll compute the numeric average. 4. Sum, add them all up, right? 2 plus 3 plus 4 plus 5 plus 6 is 20. And functions can work together. We can string them together, right? So we could take the sum of vector 1 and the length of vector 1, and we could divide sum vector 1 over length vector 1. Yeah?
When you say the function generally is the form of function and an argument there just means something that was previously like defined.
Yeah, so we could think of like vector 1 here as the object that we're passing to the function. So I guess what I said about functions take arguments, that's a little too ambiguous. Functions take an object and arguments, right? So an argument can change the operation of the function based on maybe we want, and the cases we're seeing here, we don't really need them, but sometimes we can tell the function to work in a particular way with arguments.
So you can add an argument, but
Absolutely.
it's not
There's default arguments. And the defaults are almost always sensible, so we don't need to mess with them most of the time. But functions all, so for example, the way to see what arguments a function takes in R is to use the help file. So we could do question sum. Here is on the console, if we ever just type question and the name of a function, we'll have a viewer here that says help. It'll give us the help file for sum. It'll tell us sum returns the sum of all values present in its arguments. So this ... is the first argument, but that's effectively just the object we're passing. Then there's one other argument we can give sum, and that's na.rm. Should we exclude missing values when we compute the sum? The default is no. And if you ever are confused by how a function works, if you scroll down to the bottom, there will always be examples that you can just highlight and hit Command Enter and run on the console, and it'll show you what that function does, right? So I can just run any of these on my console if I'm confused about how a function works. So the help files look really confusing at first, but once you get the hang of it, they're incredibly helpful. Incredibly helpful. Okay, cool. Now, we don't have to do one function per line, right? We could take the sum of vector 1 over the length of vector 1, because they're each going to return a single value, right? So first it's going to compute the sum, 20. Then it's going to divide that by the length, 5, to give us 4. And what is this quantity equal to? Sum over length of a vector. That's the mean, right? The sum of a vector divided by its length is the mean. So we've just kind of created a redundant mean, but that's okay, right? We could actually make this our own function if we wanted to. We're going to call it redundant mean. I'm going to use the function to define a new function. This is getting weird, but that's okay. So you can see it highlighted in blue. What we're doing is we're defining our own function called redundant mean. And I'm telling it, you're going to take a single argument called x. So when I call redundant mean, all I want you to take is x. And x could be anything, right? It's just a variable name I'm creating. Now, once I'm inside my function, I'm going to open it with the curly brace and close it with the curly brace. And then I have a batch of code in here that I can run multiple times without copying and pasting this entire block of code over and over. So the first thing I'm going to do in my function is I'm going to define n. N will be equal to the length of x. The sum of x will be equal to the sum of x. X bar, which we'll see, maybe just lift the edge of the table up a little. It'll come out. X bar, we'll see this notation as we go, but X bar typically stands for the average of a vector X. That is an X with a bar on top. There's a whiteboard. Awesome. Too bad I don't have a marker with me today. And then we're going to tell R to return one of these values. We've created three things in sum x and x bar, but I want my I want to get back out the mean. That's what I want to send back, right? So I'm going to return x bar. So when I run redundant mean on vector 1, I get 4, right? So I'm going to send vector 1 here. Vector 1 becomes x, right? So when I call this function on vector 1, it implicitly becomes x. N becomes the length of x. Sum x becomes, so this becomes 5, this becomes 20, this becomes 4, and it sends back 4. Yeah, you're not going to write a ton of functions at first, but as you get more and more advanced and you need to do specialized things in your data, you're going to need to be able to write your own functions. So we're just introducing that now. You're not expected to really be able to replicate this yet because this is pretty difficult. But when you get to more advanced data analysis, you will absolutely need to write your own functions.
You don't have to say x equals vector 1, right? You can think of it as a function.
Yeah, that's implicit because this is, so we're saying x is the argument that function x will take. And so x then within the function, right, R understands whatever I tell it in the argument will be treated as if it were x, right? So here I'm telling it vector 1 is what I want you to do redundant mean on. So redundant mean now knows that x is vector 1. I don't have to be explicit about that. Yeah.
So is this how people would create their own packages?
Yes.
Okay.
Yeah, so people do write their own packages in R all the time. A package is basically an elaborate collection of functions. Yeah. And for most of my work, I usually have 5 to 20 user created functions that I'll use for my research. And it's typically when I find myself doing the same thing over and over again, and sometimes that'll be 20 to 100 lines of code. And instead of just copying and pasting 20 and 100 lines of code over and over again, I can write a function and just call that function over and over again. Something simple like converting state abbreviations to state names, right? So if I have a list of AL, AZ, AK, right, AR, and I want to turn those into Alabama, Alaska, Arkansas, Arizona, I can write a function that will do that for me. I knew you were going to go do that. Thank you. Much obliged. All right. Okay. Questions so far? Yeah.
What does return mean?
Return tells it what to send back. Because I've created 3 objects inside this function environment, right? Return tells it what's the output I should send back. Because it could send some x, it could send n. It doesn't know that x bar is what I want. I have to tell it explicitly when I run this function, what's the output I will give to the user. In this case, I want x bar to come back out. That's the mean I've computed. So every function should have a return that is telling the computer what to give to the user after they run the function. It's usually going to be an object, maybe a single number in this case, maybe a data frame, right? Lots of different outputs possible. Okay. Any questions thus far? We're recording today, so. I realized I still have a video file. I didn't see that. Yeah. Okay. Questions so far? We're going to push forward a little bit longer, if that's okay. Maybe another 20, 30 minutes, and then we'll take 5. Everyone good with that? Okay. I'm not offended if at any point you need to step out. So just, if you need to, go for it. Okay. Data frames. We talked about this again a little last time, but we're going to take a deeper dive. If you have Tidyverse loaded, the iris data set will be loaded into your environment for you. It's a demo data set that comes with Tidyverse. So if Tidyverse is loaded in with library, if you go to your console and type head iris, you should see the first 6 lines of this data frame. Is anyone seeing this? Anyone got this pulled up on your console? Yeah. Cool. Cool. Okay. Iris. So what this is it's a collection of observations of the length and width of the sepal, which I don't actually, does anyone know what a sepal is? I don't know anything about flowers. I know what a petal is. I'm guessing the sepal is some other component of a flower. That's okay. Doesn't really matter. We're just going to play with it, right? So we have the sepal length, the sepal width, the petal length, and the petal width, and the species of flower that it is. So these are all observations of flowers. There are 3 species in this data set. And then we have, I think, like 100 or so observations of flowers. So a data frame, right? We remember that a matrix is a collection of vectors, right? A rectangular sort of grid that is a series of vectors that has rows and columns. A data frame is a matrix that has the special property that all columns have names. It also has the special property that the columns can take different types. So we notice here we have 1, 2, 3, 4 numerics and 1 character. All columns do not have to be the same type in a data frame. They do in a matrix. If we're in a matrix, it's always going to be all numeric, right? Which you could convert into a logical as 1s and 0s, but it can't be character, right? If it's a character, then it's going to be a data frame. So we have, effectively, we have variables in the columns, observations in the rows. Flower 1, flower 2, flower 3, flower 4. Flower 4, this is its sepal length, this is its sepal width, this is its petal length, this is its petal width, and the species is Setosa. Yeah? So this is the data frame. This is going to be 98% of the kind of objects we work with in R will be data frames. If you see me use the word tibble, or you see that word in the book or anywhere else, a tibble is just a special kind of data frame that works basically the same as a data frame does. It's just optimized for tidyverse functions. So tibbles, data frames, at this point, you don't need to worry about the distinction. They're the same thing. Okay. Cool. Questions on what a data frame is? Okay. So data frame is a super matrix, right? So we can obtain any element xij from matrix X. And again, a matrix will typically take on a capital letter, right? So in this case, capital X. And then our row indices will typically be represented as I and J. So xij is how we can represent an element from the matrix X. Little x for an element from matrix big X. Yeah? Okay, so what is iris 3, 4? Iris 3, 4. Can you say that a little louder? So row 3, column 4. 3, 1, 2, 3, 4. 0.2. We can also say iris 6, 2. 1, 2, 3, 4, 5, 6. 1, 2, 3.9. Right, so we can obtain any single element from a vector with a 2-position notation. Row, column. 6, 5, Setosa. Yeah.
What are I and J?
I and J are just indices. They're row and column index. So I is the row number. J is the column number.
Yeah, did you have to call that yourself? Or is that...
That's just the mathematical notation. That's not in R. So when we talk about matrices in math, we use the IJ to describe matrix positions. So that doesn't have any special meaning in R. It's just, I'm introducing the kind of symbols that you'll expect to see. Does that answer your question or not exactly? What are you thinking?
I call the title when I call the XIJ, for example, X32.
Mhm.
Should I call without the title?
The title rows are not a row. Yeah. So in a data frame, that's a good question. The data frame has a special characteristic where each column has a name. Those are not rows. So you can see that row 1 starts here. Yeah. So, and if we want to retrieve the names of a data frame, we can use the names function. So we can say names of iris, like so. And it'll give us those column names. But if I ask for iris row 1, it will not give me those. It will give me the names because it always will give me the names just so I know what I'm looking at. But it's going to give me that first row of observations. It will give me those names if I put in row 2 as well. Okay. That's just R being nice. Okay. So iris11 is 5.1. Iris22 is 3, right? We could keep going through this. We could also use, we can leave one blank. So we could say iris blank comma 1. What will that retrieve? What does this give us? The first column, because it's row, comma, column. So this will give me all of column 1. Right? So this will give me the 150 observations for column 1. 150 unit long vector. Iris 1 comma will give me what? Row 1. Row 1, column, all of them. If I leave it blank, it will return all of them. If I use the $ notation to call out a column by name, iris $ petal dot length, I will get the entire column for petal length. The $ notation works equivalently if I don't know or don't remember the column position, I can use it by name. In this case, I think petal length is column 3. So iris comma 3, iris $ petal length will return the same thing. Yeah. Technically, what it does is R works with some objects called lists, and a data frame is a special list. The $ calls elements of lists. And so the $ notation is technically saying, go to the object iris and take the thing from iris called petal length. But yeah, it's just a syntax memorization thing. But let's see what we could do. So iris, the names of it. So petal length is number 3. So if we do iris bracket comma 3 equals iris $ petal length, what do we think we'll get? Someone predict what this command will return. How many? It'll return 150 truths. It will compare every element of one vector to every element of the other vector. It just so happens these are the same. Right? But let's change it to 2. None of them are the same now, right? So it'll do a comparison of each single element of the vector to each single element of the other vector by row index position. Right? It'll take 1 compared to 1, 2 compared to 2, 3 compared to 3. Which, when we think about it, that's actually like a fairly complex operation. We've just asked it to do 50 equality comparisons, or 150 equality comparisons in one line of code, right? So we've kind of condensed a lot of that complexity down. Okay, other means of indexing, we can, instead of saying 3 comma 3, we could say, go to the petal length column and give me element 3. So what's this going to be? What is this calling in terms of what's in the data frame? The third observation of petal length, right? Could be 10, could be 27, could be 150, right? But we can call out each single observation from this vector with an index. We can also explicitly use column names in bracket indexing if we wrap them in quotes. So we could say, call out row 1 from the column petal length. This is getting silly. I recognize I'm showing you like 50 different ways to do the same thing. This is just to kind of get us thinking about how these things work. Typically, we're not going to go and do it 40 different ways. Typically, we're just going to call it out with the $. This is typically how you're going to work with it. Right? But there's all these other ways we could do it. Okay. So indexing, there are some convenient functions that we can use on data frames like summary. Summary will give us, if it's a numeric variable, will give us 6 values for a numeric vector. It'll give us the minimum, the maximum, the first quartile, the third quartile, the median, and the mean. The median is the 50th percentile, 50th quartile. We'll talk about quartiles and stuff later. That sounds familiar to you. but you can see that it'll give us a really quick overview of what's in the data frame. It'll tell us if it's a character vector, what are the values in that character vector and how many of them are there. So it'll count how many of each value there are. Summary is a really great way if you don't know what you're looking at in a data frame. Just get an overview of what's in here, right? It'll tell us for every single column in the data frame, descriptive statistics or a count of values. Summary is really, really useful. You will use it all the time. In row is another one that's very useful. How many rows are in the data frame? In col, how many columns are in the data frame? So that's number of rows, number of columns. Dim stands for dimensions, if we want to get rows and columns at the same time. Head, we've seen a lot already. Return the first 6 rows. That's a really great way, in addition to summary, to just see like what's inside this thing, right? What am I working with? Head is typically what I will do to just remind myself what is the structure of the object I'm working with. Tail will take the last 6 rows. Maybe I think the top and bottom of it look different, right? So instead of getting the first 6 rows, I'll get the last 6 rows with tail. Names, we just discussed. It'll pull off the column names. We talked about mean and sum, right? We can do those over data frame columns. So we can compute the mean of a column as you did in your homework, right? Mean iris $ petal length will give us the average petal length for that flower, or across all flowers. Sum, and then, you know, I'm doing my redundant mean again. They'll give us the same thing. We could divide the entire column by 2, as we've already done with the constant. And we can take a break. And then we'll come back and we'll jump into Tidyverse. Because if you didn't think this was confusing enough, now I'm going to tell you different ways to do all the things I just showed you how to do. It's going to be great. So I have 11:01, come back at 11:06.
Don't ignore the screen. It's very dirty. Do you like it? Yeah, I love it. It's just modest. Like the windows. I just have everything on that. But I guess like what if you feel like it's in the things you get it and you will take it and fast enough. Like sometimes like because when I work with art, like I work with art.
Zoom recording. Okay, so now we are going to introduce the Tidyverse packages. So we've been loading them and using some things from them. ggplot is included in the Tidyverse. It's a series of packages mostly written by a data scientist named Hadley Wickham, whose data science book you will read for this week's, at least a chapter of it for this week's homework. But he wrote ggplot, he wrote a lot of the Tidyverse packages, and they all share a philosophy that's really similar to some of you may have been exposed to SQL or SQL, the database management scripting language. And the philosophy behind Tidyverse is really similar to the philosophy behind SQL. So learning Tidyverse will actually improve your data chops in other areas too, right? Because then picking up SQL to do database queries won't be that hard for you because you will have seen the ideas before, right? So it's a really efficient way to work with especially large data frames, large collections of objects where we have lots of rows and lots of columns, which describes most of the data we work with. You know, in CJ, if you go download from ICPSR, if you go download the Uniform Crime Reports data, it's got, I don't know, 70 or 80 columns and a few thousand rows in it, right? Most of those data sets have hundreds of columns and tens of thousands or hundreds of thousands of rows, right? And so we're getting into large objects really quickly, and using the Tidyverse packages makes your life far, far easier when we need to work with large objects. I didn't learn Tidyverse until the end of my course through grad school because that's kind of when it rolled out. And I wish I'd started out with it because so much of the stuff that I did in data analysis in base R is so much easier in Tidyverse. And so instead of kind of getting started in base R, I think it makes sense to just go right to Tidyverse. It's a much more efficient way to do things. Okay. You go away. Where do I just make you go away? No. Whatever. Okay. So basically everything you ever write in R will have this as your first line of code. We are almost always going to load in the Tidyverse package. I think it is actually the first line of code in everything I write. It's just to load it in. So just get used to doing that. And if you're writing an R markdown document, your first chunk will call your libraries in. It'll almost always call Tidyverse in. Maybe it'll call a few others as well, but for now, Tidyverse is going to have what we need. Okay, so let's introduce some core functions from Tidyverse. We're going to start with a series of functions so Tidyverse is a collection of packages. It's about 12 packages. One of them is called dplyr, and there's a handful of functions from that package that are going to kind of do the backbone of the data manipulation work that we do in Tidyverse. Filter is the first one we're going to use. Filter allows us to pick observations based on their values. So rather than thinking about column indices and matrix indices and all that stuff, we're just going to name variables, right? Sepal length. And then we're going to filter based on, let's pull all those observations that are equal to 5.1. So take the iris data frame, and then within iris, find me all observations of sepal length that are equal to 5.1 and return only those. Filter the data frame based on this condition. The condition is sepal length equals 5.1. So we'll see that I get 9 observations where the length of the sepal is 5.1. It returns a data frame, right? It returns a 9-row data frame that's a subset of iris. A subset is something that is a collection of elements from a larger object, right? We'll get into the kind of set notation stuff, set theory stuff later, yeah.
What happens if there's no object?
It'll return an empty object. It will return nothing. I mean, it will return an object, but it'll be empty. Okay, so filter allows us to pick observations based on their values. Now we used equals there. We used the equality operator, double equals. We can also use less than, right? So filter iris for sepal length less than 4.5. So I want only those with small sepals. I get 4 observations when I filter that way. Maybe I want it to be greater than equal to 7.7. So now I get the big ones. I get 5 objects back there, 5 observations. Each of these is a data frame, right? So I can store this in something. I can call this B, right? So we could say B is filter iris sepal dot length greater than equal to 7.5. And now when I look at B, let's take a summary of it, right? That's what B looks like. It's six observations compared to 150 in iris. So we've subset iris for only those observations that have a large sepal, right? And that's 6 observations based on the value I set. But that's a subset, yeah.
How did you get B to equal that filter, those filtered?
I used this line of code, an assignment operator. So here, I'll show you that again.
So it's all the same, just with the B equals at the beginning.
Yeah. Yep. The only difference is I assigned this to B. Right? I created a new object B and said, inside of B, put this. Yep. And if you want to cycle through commands on the console, up and down, do that for you. So you can go through your command history on the console just by pushing the up and down arrows. It can be really handy. Cool. We could give it 2 arguments at once. We could say filter iris, where the species is versicolor, and the sepal length is less than 5.5. So it'll return only those versicolors where the sepal length is small. 6 observations. This effectively says species is versicolor and sepal length is less than 5.5. If we wanted to get fancy, instead of the comma, we could use the ampersand or the and symbol. That would do the same thing. Can anyone guess what this one does? Not equal. Exclamation equal means not equal. The exclamation sign in R means not. So this says return only those species that are not setosa. It's going to drop all the setosas and return the versicolors and the virginicas. We can't see those because there are too many observations to display on the screen, but that's what it did. So anytime we see the exclamation mark in R, that is not. It also computes a factorial, but we'll think about factorial. Don't worry about that for now. So if I were to say, for example, they want to guess what this is going to do? False, right? True. Yeah.
So for the filter iris is not equal to if you wanted to then ask it to about this kind of frame, the easiest thing to save it as a new object.
Yep. The only reason I'm not here is just to display it. That's absolutely right. Typically, we would store these things and then do whatever operations we wanted to do on them. So typically, I would store them as B, or I would, I like to be a little more verbose, right? So in this case, we're saying this iris not setosa. So we'll say this not setosa. We'll create a new object called not setosa. That's a filter of iris where species is not equal to setosa. I didn't capitalize species. You can see object species not found. It's because I used a little s, right? So I can rerun that command, fixing species here, and then setosa, you'll note I capitalized it there and it shouldn't be capitalized because it's not capitalized here. These are the small little things that you're going to screw up all the time that will drive you absolutely bonkers when you're starting to write R code. This stuff will drive you crazy. But you'll learn how to read these errors and you'll learn how to look for the kinds of mistakes that will trigger these kinds of errors over time. It just takes practice. I guarantee you, you're going to like bang your head against the computer for like an hour not knowing why it's not working, and it will be that you didn't capitalize the S when you should have capitalized the S. But now you could do it for 10 years and still make those mistakes. Anyway, here's not setosa. And it's going to, instead of iris, right now we have this thing that drops all the setosas. The number of rows in not setosa should be 100 because there were 50 of each and we dropped one of them. Yeah. So yeah, typically I want to store these somewhere so that I can do work on them later. And you can name them whatever. I like using the underscore to name objects, not setosa, but there's no reason you couldn't make it like not dot setosa or, not or use caps, not Satosa. You'll figure out your own style, right? It doesn't matter when we're naming objects, use capitalization, underscores, or periods. Those are the good ways to separate words. Can't use spaces, right? Spaces are not allowed in object names. Okay. Other questions on this? Filter is pretty straightforward. Okay. Arrange. Arrange is the next verb we're going to introduce in Tidyverse. Arrange reorders rows based on values. So we're going to take the column sepal width. We're going to arrange them. So what arrange is going to do is it's going to sort all of the values in the data set from lowest to highest by sepal width. It's going to reorder the rows of the data frame based on the value of sepal width. It's going to keep the rows together, right? But it's going to re-index them based on their value of sepal width. So it's going to take the smallest one, move it up here, and the largest one, move it to the bottom. Arrange is pretty straightforward. In Excel, it's like sort A to Z, right? If we've used that function in Excel. We can also make it a descending sort. So by default, it's an ascending sort, means it goes from smallest to largest. If we want to go from largest to smallest, we just need to wrap sepal width in this function DESC, which stands for descending. Now we can see that we go from the largest sepal width to the smallest instead of the smallest to the largest. The range is pretty straightforward, yeah? Okay. Select allows us to focus on a subset of columns. So select, we're filtered based on row values. Select will return only those columns that we explicitly name. So if I want a subset of the data that is only 2 columns, instead of the 5 columns that are ordinarily in the data, I can select from iris species and petal length. It will return them in the order I asked for them. So I'll get species and petal length. It'll drop the other 3 columns that I did not ask for. They're still in iris, but they're not in this object. When I say drop, it's just what it's returning to us now. It didn't delete iris. It didn't touch iris, unless I explicitly told it delete iris with this, right? Which I could. So select allows us to name the columns we'd like to see. We can also use minus notation to drop columns. If we want to say, I want all the columns except for this one, I could say I want everything in iris except for sepal length and sepal width. I'll put a minus on sepal length, a minus on sepal width, and then I'll get the other 3 columns back. And I can combine, I could say I want species, and then I want everything but the other one, right? I can have, you can combine minuses and not minuses in select statements. It's kind of weird to do that, but you could. So select returns a subset of columns. Pretty straightforward. Rename renames columns, does what it says. Maybe I don't want to call species anymore. I want to call it type. I'm going to rename in iris. I'm going to rename the species column to be type. You can see that that column has a new name. Cool. Mutate, now we're getting fancier. Mutate adds a new column, and it can be functions of existing columns. So in this case, I want to make a new variable called petal size. I'm going to mutate iris. I'm going to add a new variable called petal.size that is equal to petal length plus petal width. So it's going to take these 2 columns, add them together, and create a new variable. Mutate could take a constant, much like our $sign assignment we did with pop 1000. This is the same thing, only we're going to use the mutate function to name our new variable and then describe the operation that's going to define it. No reason we can't add multiple variables at once in a mutate command. We could say petal size is petal length plus petal width. You could say sepal size is sepal length plus sepal width. And then we could compute the petal sepal ratio as petal size over sepal size. It doesn't actually display it because we ran out of room on the screen. But we could refer to variables we create in sequence. Right? So what we've done here is we've defined petal size as a function of petal length and petal width. we've defined sepal size. And then I'm going to create another variable that's a function of the two I just created. Does everyone see how we are kind of nesting this? So the order matters here. I'm creating two new things, and then I'm going to use them. Questions on this bit?
Before I want all this together, if I put things that I'm gonna use at the end of the thing, is it okay? So should I put the first and second one up in the if I want to use that one in the downside of the thing?
Yes, they need to come before when we're going to use them. So yeah, the order does matter here. We could store it and then come back and use it, right? But let me just show you. This will look like. So if we run this, we'll get, it's a bit wonky because it's too wide, but yeah, it's still too wide. To display on the screen all at once, that's okay. There we go. So we can see that it computed pedal size first, then sepal size, then the pedal sepal ratio, which is the ratio of these two. Right? So at first it computed this, then it computed this, then it computed this, which is the ratio of these two. But there's no way it could compute this without first computing those two. I could have folded them all into the same call, right? I could have said, yeah, but I think does the sequencing make sense? Yeah, okay. Like in theory, I could have just folded this all into one call and said, right, pedal width plus pedal length over. This was a little wordier than it needed to be in theory, right? That'll do the same thing, but it's fine to name them and then work in sequence as well. Okay. Other questions on mutate? Mutate creates new variables. Okay, now where we get cool is Tidyverse can string together multiple commands. It uses what's called a pipe to do this. So this pipe operator is just the percent greater than percent. It's a weird little symbol, but if we put this in our code, it will execute multiple commands in sequence as if they were all one command. If you want to make a pipe on your laptop, you can use Command-Shift-M on a Mac or Control-Shift-M to make the symbol, because it gets tedious to type percent greater than percent all the time. But if I do Command-Shift-M, it will make my pipe. Pipe, 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 pipe. Okay, so the pipe strings together commands. We already saw this philosophy with ggplot, right? We use the plus to link together functions in ggplot. The pipe is identical, but it does the same thing as the plus in ggplot. It just is a different symbol. So here's what a pipe does. We're going to take iris, and first we're going to filter. Subset it to only versicolors. Then we're going to select 3 columns. Then we're going to create the sepal pedal ratio as the sepal length over the pedal length. So we're going to return these 3 columns with this new variable only for versicolors. So we did a filter, a select, and a mutate all in one call to the console. Did them all simultaneously. Well, in sequence, but we can link them all together. Now notice I did something different here. Instead of saying filter iris, select iris, mutate iris, I said take iris, pipe. What that will say is use iris as your object. Okay, so first start with iris, and then onto iris filter. And then onto whatever results from iris filter, select. and then to whatever results from iris filter select, mutate. Right? So the pipe allows us to just name our object and then list the functions we want to apply to that object. It allows us to write really efficient code. So instead of having to make 3 different assignments for the filter, select, and mutate, I can do it in one. So piping is going to become your nemesis and your friend. Eventually your friend. But where piping gets really handy is when we want to transform our data in particular ways. So this is useful, right? Filter, select, mutate to do multiple data manipulations at once. But where we're really going to see this take off is when we use summarize. So summarize uses a variety of summary functions over some specified data. So first I'm going to take iris, and then I'm going to pipe onto iris to summarize. I'm going to say summarize iris and create 3 new variables: mean petal length, min petal length, max petal length. It's going to compute the mean, the minimum, and the maximum of iris and give me a new data frame that has those 3 variables. So we have a new object that has mean.pl, min.pl, max.pl with the values of each. So we use functions like sum, mean, max on vectors before. Summarize does that. It takes a vector and returns a single value, right? It's not like a mutate where a mutate returns a whole column, right? It applies it over the entire vector and returns a vector of equal length. The mutate will return a vector of equal length to what it takes in. Summarize will return a vector of typically shorter length. And in this case, only 1. Sometimes it'll return more than 1, but I'll show you that case in a second. Okay, summarize. Sometimes you'll see me write summarize with an S. It doesn't matter if it's summarize S or summarize Z, it'll do the same thing. It's because the guy who wrote it is from New Zealand, so he has like British English sometimes. But anyway, it works with a Z or an S. Okay, summarize is more powerful with its best friend group by. So what group by does, says take iris, group it by species. So typically we're going to use group by with a categorical variable or a character. In this case, we have a natural organization to the data frame already, right? The data are grouped by species, right? We have species are a natural grouping. We expect species to be similar to each other. So let's group them by species and then compute a summary. And now what do we get? For each species, we get the mean, the minimum, and the maximum. This is incredibly, incredibly powerful. I can't understate how powerful this is. For doing complex data analysis, this right here is an incredibly powerful tool. Yeah.
If you wanted to do what about for the mean dot, so mean.pl, you created an object in the summarize function, right?
That's correct.
You wouldn't have to save it again as something. It's just
Well, so I could store it as an object.
okay, so it's not already stored as an object there.
No, it's not. I was just calling it to the screen to show it, but we could definitely do this, right? I'm going to call it my new object. And now in my new object, I have 3 columns and 3 rows, right? And I could take the mean.pl column out of that. It's a data frame, right? I've created a 3 by 3 data frame where before I had a 150 by 5 data frame. So I've reduced the dimensions pretty dramatically. But I've gained a lot of good summary information. We could also use group by, let's say we only want to look at like those flowers with a large sepal, right? So we could say group by sepal.length greater than mean sepal.length. So what's that going to do? What's this group by going to do? This one's kind of tricky. It's going to split the data into two. Half of the data, well, not, it won't be exactly half, but we'll have one subset of the data where sepal length is greater than mean sepal length is equal to true. That is those flowers where the sepal length is larger than the average across the data set. And then one group where it's false. So we're going to create two groups in the data, those for which this statement is true and those for which this statement is false. And then we're going to summarize these values for both of those groups. So let's see what that looks like. So I've now created two subsets of the data, sepal length greater than mean sepal length. So this is what those that have a smaller than average sepal length. And these are those that have a larger than average sepal length. And we can see what the differences in petal length across differences, those two groups for sepal length are. Right? We could get crazy with this grouping function. We could do lots of creative things with it if we have different kinds of questions we want to ask about the data, which you will get to explore some on your homework. Okay. But typically we're going to just use, when I look at the data, I'm going to look for a natural grouping in the data. In this case, species. Species is a really easy, a categorical variable is typically a really easy way to group. Categorical meaning something that in R will look like a character that takes on multiple groups that represents a qualitative difference in units, right? So species is a qualitative difference. It's not the same across units. And that's typically what we're going to do. If we remember the Gapminder data, we could do something similar there. Let's say we wanted to look at change in life expectancy over time across the world, right? So we could say head Gapminder, just to remind ourselves what's in the data. And let's take, we'll call it life exp time series. I'll take a Gapminder and I'm going to pipe onto that, Control-Shift-M, group by year, pipe, summarize, life exp equals mean life exp. Let's take a look at what this gives us. Now we get the average life expectancy for all countries in the world over time, right? And then we could plot this to see what's going on with life expectancy over time. Sorry, your question? I'm pulling in external data.
Okay.
The Gapminder data is included in the Gapminder library. So it's just a data frame that I'm calling it. I could do this with any other. It's just the time structure makes this kind of operation a little more sensible to do. So let's make our time series plot. I'm going to call my data frame object that I'm plotting. I'm going to make my aesthetic arguments. I'm going to say X is equal to year, Y is equal to life expectancy. Then I'm going to make my what's called a geom, or I'm going to add a layer of information onto it. And I said line, but let's actually, our points, let's actually make it a line plot. And let's look at that. So that's what life expectancy is doing globally over time as an average of country life expectancy. So we can see a really clear increase in life expectancy around the world over time. However, maybe we think things might be different across continents. So instead, I just copied and pasted these bunches of code. So I'm going to put a comment here. Let's look at differences across continents. So instead of grouping just by year, I'm going to group by year and continent. So I can group by multiple variables. If I have multiple levels in the data, multiple kind of natural groupings, no reason I can't use those. So let's look at what this data frame looks like now. Now I have an observation for each year in the data for each continent. So instead of, here I had 12 rows. Now I'm going to have 12 times the number of continents that are in the data, which is not exactly equal to the number of continents in the world because they collapsed the Americas. But there's going to be 60 rows in this data frame instead of 12, right? Because there are 5 continents in the data times 12 years possible. So we get 60. So now we can make our plot a little more complicated by adding in a color for the continent to look at differences across the continents in this time series. And we're getting into pretty sophisticated data visuals already, right? And so now we can track what's going on. Now we still see this kind of monotonic increase, but we can see that life expectancy in some places had a far lower intercept, right? It started at a far lower level than it did in other places. And we can see that the slope across continents is relatively similar until about 1985, and then it levels off in Africa, right? And life expectancy plateaus there for a few years. And there's almost certainly differences within Africa, right? So we could look at countries within Africa to see, I guarantee you what's happening here is war, that there are some places where there were high levels of war, and that suppresses life expectancy dramatically. Okay, but we just made a pretty cool data visual with group by summarize, and this, hopefully, we could, no reason we couldn't do year by continent by country, right? And we had our 60-row data frame before. Now we're going to have 12 years times the number of countries that are in the data in our data frame. Actually, that's just what we already know. That's actually just returning. That doesn't do anything. Sorry, I'm going to stop myself. That doesn't do anything because that's already the level of the data. The data is already at the country year level, so I can't go under that, right? Okay. Group by summarize, super powerful. Do we feel like we have an okay handle on that? Of all of the techniques that we've shown you today, this is without question the most complex, but also the most powerful. Because now we're not just creating like subsets of the data that are like additions of 2 columns or things like that. We're actually reshaping the whole thing, right? We're turning it into something else. So output in R. We're going to do a couple more things and we'll call it quits today. Okay. Okay. Sorry. Something from my child's daycare. Okay. Output. So the most straightforward way to deal with output in R is to write to a file. So we're typically going to work in R with delimited files, which are plain text files in which values are separated either by a tab or a comma. The commas are going to be the most common one we use. So you can see here that what I do is I take my iris summary object, the same thing I just constructed over in RStudio, and I'm going to write it into a CSV file. A CSV file stands for comma separated values, and it's effectively a very simple spreadsheet. This is going to be the most common data format that you work with. There are others, but CSV is a very simple and very common data format. So let's see what that does when I take, for example, my new object from up here, right? The iris object. So this is what's in it. And let's produce a CSV file. First, I'm going to tell it what object I'd like to write. I'm going to use the write_CSV function to do this. So I'm going to tell it, I want you to take my new object and put it in the file, my cool file.csv. Now, I also want to know where that's going to go. So I'm going to type get wd on my console so you can get my working directory. Usually I'll set it with a project. We'll talk about project management later. Right now, I'm just in my users folder, but so let's actually make this /box. So I can give it a full file path to tell it where to go. And I want to put it in my intro stats folder. So I'm basically telling my computer to go to my root, go to Dropbox, go to teaching, go to intro stats, and then put my cool file there. as we get further into R, it's incredibly important that you keep a stable file, a directory structure. So like do your work in one location, one folder on your computer, and keep everything organized there, right? Instead of putting stuff on your desktop and in your documents, wherever, work in the same location. It'll make your life a lot easier if you have a stable single place that you're doing your work in. Yeah, so keeping a consistent file path is pretty important. But let's write the CSV object. So what I just did was I took an object from R, I took this from R, and I wrote a file to my computer. So if I go to my teaching, my R, my intro stats folder, where I have all my slides and everything, I told it to remember to write to Dropbox teaching intro stats. And there's my cool file. And you can see that I can open this in Excel. And there it is, right? It took that, it put it now, and of course in Excel, the first row is going to be the names and the column and the row names, but those are the values. The other thing we can do though, we don't need to work with Excel to do this. It's also just a text file. So Excel files are actually like a complex, like you can't open them with just a text editor and view them. But a CSV file is just a plain text file, meaning all that's in it is text. So often what I want to do, I use an application called Sublime Text for my text editing, but you could use Notepad or anything else. This is what that file looks like. That's it, right? It's just a collection of column names separated by commas, and then values separated by commas. And our software knows to render that as a spreadsheet or as a table, right? That's what comma separated stands for. That's what a CSV file renders as when we load it in. But that's the whole file. And this is really efficient because you can see it's only 95 bytes of storage on my computer versus if I were to save this as an Excel file, which Excel is going to want me to do, it's going to be like, are you sure you want to work in CSV? Don't you really want to work in Excel? I'll be like, no, Excel, I don't. But you're going to hate Excel by the time you get through with my class, hopefully, because it's not an efficient way to do data analysis work. But look at this XLS file, as opposed to being 95 bytes, now it's 10 kilobytes, right? So the size of the file increased by like an order of magnitude. It increased dramatically because now there's a bunch of other garbage that gets stored in there. And I can't open this as a text file anymore. It won't make any sense. Let's try and see what gobbledygook I get. It won't make any sense though. Whoa, what's that? Right, that's not my file. It's now like 627 lines of whatever that is, as opposed to 4 lines of that. So this is far more compact and efficient than storing things in an Excel file. Okay, it's not the most compact way to store data, but it is more compact than Excel. Anyway, that's one way to output is into a file, right? And what that does is because like whatever we do in our environment, when we quit R, it's gone, right? I mean, so we have our script and we can run that again and recreate those objects in our environment. But the way that we could like actually make this permanent would be to copy and paste it into a Word document or something, or write it to a file so we have it for later reference. But the reason that I want you to use R Markdown is it makes this task much easier. We can still write stuff to files, but the reason to use R Markdown is it combines the data analysis and output parts together, right? We don't need to think about these as separate tasks. We don't need to save our plot somewhere and then paste it into our document. Instead, we can just render our plot directly in our document, right? So it takes a lot of the complexity of taking output from R and putting it into our writing. It basically removes those boundaries. We don't need to think as much about file output. And we don't need to think about copying and pasting anything, right? Yeah.
So when you're submitting like your data for, like when you were saying the study you did,
yeah, that
someone found an error, you would submit an R Markdown.
Actually, I submitted it in LaTeX, but that's neither here nor there. But yes, but it gets more complicated depending on the journal. But okay. I did write my entire dissertation using R Markdown.
Okay.
So that's definitely doable. And it's how I like to start writing. It's how I like to write my papers, because I can kind of write what I think is happening. I mean, I can get quite fancy and include citations. I can do like full bibliographies within R as well. We'll cover that in more detail when we get to advanced. Let's do basic R Markdown first. But yes, you could write entire journal articles using R Markdown, and they can look quite good. They can look very professional. Actually, I can, whatever. I'll show you one later.
Specifically, like if you're submitting it for like the reproducibility aspect, like you would probably rather submit a Markdown file, like rather than submitting just a regular R script.
Yeah. So like this is a open access version of the paper I'm working on. This was written in R Markdown. And you can see it looks like a professional paper, right? It has an abstract, it has headings, it has full citations, and it has a bibliography at the back. It renders math quite nicely, and it puts my plots right where I want them. I didn't have to copy and paste anything. My code, my data analysis, and my writing are all in the same place, and I can just render the whole document at once. Anyway, yeah. So, I mean, this looks like something we just made, right? These plots, but then you can get fancy and do stuff in ggplot like this, where you can make line plots by state, right? Well, if you want to get fancy with it, we can get fancy with it. I'll stop showing off now. Okay. So, yeah, I love R Markdown. It really, if you're going to work in R, it, I think, should be the way that you do your writing. You'll have colleagues that want you to write in Word, but check it out. Maybe some of you noticed the options on knit. I have three. I have HTML, PDF, and Word. So if I knit this to Word, it will create a Word document for me that renders my code, that renders the output from my code, that renders my plots into a Word document that I can just save, as opposed to worrying about whether I type my tables correctly, right? And we can do a lot more to make the formatting prettier as we go. We're going to start not worrying about whether it's attractive. We'll make it attractive later. Okay, so R Markdown. Okay, so yeah, with the proper workflow, we can do it all. Let's work through some demos. So we saw with the homework, right, we have our code chunks. What I want to show you now is a little bit more about text formatting in R. We kind of got some experience playing with code chunks, rendering graphics, that kind of stuff. But let's actually like work on presentation. So if you do a new, if we go to File in RStudio, new file, R Markdown, it's going to first prompt you, what are you trying to write? And we have a lot of options here. We're for now going to do HTML because that's the simplest thing we can do. If you'll notice, if you like rendered, if you knit your HTML file, you can open it in your web browser and look at it, and it's going to look like a web page, right? And that's nice. You can also open an HTML in Word, and it'll render as a Word document, no problem. PDF is what I typically use for academic papers, but it requires some extra software to compile. We can get there later, or we can use Word, right? But we'll stick with HTML for now. We can also create presentations using R Markdown. And in fact, you'll see my slides for lecture are written in R Markdown, right? But we're going to just stick with the document for now. Okay, we can give a title and an author. Cool. Yeah. Okay. And then we have kind of this first thing that's going on. This first chunk here says knitter ops chunk set echo equals true. What the hell does that mean? What that means is it's telling for each chunk of code to set the argument echo by default to be equal to true. What echo will do is echo will print your code in the document. So if we want to see the code in the document, we can leave that alone. I need to save it before I knit it. So we'll call it temp. If I remember to delete it later. Yeah, cool. R markdown. And you can see that when I ran the summary cars argument, when it ran the summary cars chunk of code, it actually printed it. But what would happen if I turned echo equal to false? If I make echo equal to false, I'm not going to see the code. I'm just going to see the output. So for our purposes, we're doing homework. I want to see your code. But when I'm writing an academic paper, I definitely don't want to show my code, right? Because it's massive and monstrous, right? I'm going to give people my code if they want to see it, but I don't want it in the paper, right? So I'm going to never echo my code in a paper. But in a homework assignment, absolutely, I want to see your code. So we can toggle echo on or off based on whether we want to show our code. Now, we can also do that individually. You'll see here that it says include equals false after it names the, so we have, well, let's look at cars. So what we did before was this. We just said, here's an R code chunk, run a summary of cars. Cars is a data frame that is built into R that we can just run a summary of. If I really want to help organize my code, I can name each chunk. I can give it a descriptive name based on what it does. So in this case, they called it cars, right? I usually don't name my chunks, but it's something you can do if you like. But you'll see here, we can also choose individual arguments to customize our output for individual chunks. In this case, we can override echo equals true by providing the argument echo equals false. So there, this line of code will not print in the output because I've given inside the curly braces here, the argument echo equals false. There's a lot of different options and arguments we can pass to code chunks. We won't review them all, but one good thing to do if you get confused by this is to go to help, cheat sheets, R markdown cheat sheet, or R markdown reference guide, and it'll give you a lot of details. Here are a lot of options for the code chunks. Echo, error, eval, include, message warning. Yeah.
So you have to say do it in the whole document, but then you can overwrite individual ones.
Include, so here it's saying don't include this particular chunk. It's not saying the whole document.
Okay, so but then so that after you overwrite it in the lower one, then you would have to then notate true on every other following chunk?
No, because no, it's a good question. It does not set it globally. It sets it only for that chunk.
So how do you distinguish between a set globally?
Ops chunk.
Okay, and then my second question is,
Usually, let's just like pretend this doesn't exist. And usually when I'm starting a new document, I just delete that because I want to control it myself.
and then also for like libraries.
Yes.
You don't have to again reference the library.
No. No, it's going to run the code in sequence through your R markdown document, and it's going to create an environment where whatever came before stays in the environment unless we explicitly remove it. So it's going to run just like an R script where it'll run the first thing first, the second thing second, the third thing third, and create an environment where those objects persist. Yeah, so it's not going to, every code chunk, we don't need to call libraries. So the first thing I'll typically do in a new R markdown document is call my packages. So library tidyverse. And I do, so if I just run that as you did with your homework, we're going to get the tidyverse output, which is like not especially useful for a document, right? So if I put echo equals F, what's gonna change? What'll change if I put echo equals F as an argument is that it won't have the library tidyverse command displayed, but it still shows me the output of the library tidyverse command, right? What if I don't want to see that output either? That's where include is useful. Include is useful if I don't want to see the output, but I still want to run the code. So in this case, I want to call in the tidyverse package so I have it available for my code, but I don't want to see the confirmation message that tidyverse successfully loaded in my document, right? I want it to run the code, but I don't want it to be in the document. I want it to be in the background. Include equals F does that. So include equals F means run the code, but do not put the output into the document. So this right here, these 3 lines will probably be like the first 3 lines of your R Markdown body of your document. Now, they're not going to be the first lines of it formally because we actually have this stuff up top, right? This is called a YAML header, a YAML header, and it takes a few different arguments. It can format some global variables for the document. So title has special meaning, author has special meaning, date has special meaning, output has special meaning. It gives kind of instructions to Markdown about things to do in the document. There's other things we can put in here like abstract, like institute, if you want to list your institutional affiliation, right? There's lots of different arguments we can put in this header that will affect how the document works. I told you I made bibliographies. This is where we can control that, right? We're not going to mess with it too much for now, but as we get more advanced, we'll start to add things to this chunk of it. For now, just modify the title, author, date, and you're good to go. We'll do more with it later. Okay, so let's do some formatting. I noticed some folks in writing their R Markdown used the hashtags as if they were comments, right? So we have a little bit of a distinction here that inside of an R chunk, this is a comment, but outside of an R chunk, this is a section header, right? So we can see now when we use, it uses a nested section indexing. So a single £sign is header 1, 2 is header 2, 3 is header 3, 4 is header 4. So it kind of imposes a structure on the document if we have sections and subsections, right? So we can use £sign for header 1, 2 for level 2, 3 for level 3, 4 for level 4, etc. And we can generate a table of contents based on this too, right? If we want to. If our document gets long enough, there's actually like a whole software package for writing books in R Markdown, which is kind of nuts, but actually brilliant. But anyway, you could like organize chapters and then sections within chapters and all these things. Okay, so we got a section header, right? And so level 1, let's say, typically for like homework, what I might want to do is do like question 1. This is my answer to question 1, right? If I knit that, it'll have, let's say my title is, oh, did it? I don't know why my title didn't render. There it is. Okay, my cool homework. Yeah, question 1, right? And so this can help us structure the document really easily. Say question 1, question 2, right? And then we can type our text between these headers. So this becomes a really kind of easy way to structure the document. And then within that, we can put our code, right? So 2 + 2, 3 times 3, a is equal to 2, a cubed, right? And I'm just using Command-Option-I to make my code chunks. And there we go. We've rendered everything all in line. Kind of at this point, that is just about all the formatting that I want you to worry about is just headers and chunks. If you really want to, like, because I feel like one thing that happens to our writing is like, with what something like Word is called a WYSIWYG editor or a what you see is what you get editor. And you get really focused on formatting. when you work in a format like that. You're like, oh, but that tab doesn't look right. Or like that font size is off, right? And you get really into the presentation of the thing on the screen as you're writing, as opposed to being focused on the text. And what I love about working like this is it strips all that out, right? And it says, all I'm worried about here is I'm in this section and I'm writing these words. And I'm not going to worry about what it looks like until the end, right? And then I can think about formatting all at once. I don't have to think about it the entire time I'm writing. For me, this is a much more focused way to write. Writing in plain text or markdown to me is a huge improvement in productivity, just in terms of focus. But you know, we'll all differ there. Yeah.
So given that you already have kind of a setup for the homework, do you want us to do like create headers for different questions?
Yeah. So like in the future, I don't actually give you an R markdown file this week. I'm just giving you an assignment. So you're going to need to create your markdown file. So yeah, I would like headers for each question. I mean, whether you use 2 or 3 or whatever, I don't really care, but I want it to have a structure and I want it to be readable. Like you're writing a report that you would hand to somebody and you want them to understand what you're doing. Okay. Like our goal here is to like do scientific writing in a way that other people can read. Yeah.
I thought we got the like template for every assignment.
Sometimes I will, sometimes I won't.
Okay. In
this case, I won't, but most of the time I will. And when I do, I'll give it usually to you broken down. I didn't last week because I didn't want to get confusing. But okay, minimally, if you want to do some formatting, we could do things like this is italics, wrapping something in 2 asterisks. We'll make it italicized, right? Wrapping something in 2 asterisks, we'll make it bold. Yeah. Maybe we want to say question 2, item A. This is a sub-question. B, this is another sub-question. C, yet another. I can use the minus symbol separated by enters to create a bulleted list. And that'll render just like that. So that can be handy. Or I can just do one to do a numbered list. It will work. Doing a numbered list that way too, it'll be indented and organized, right? So those, as far as what you need to do to get started, that's about it. Like I think bulleted lists, numbered lists, bold italics, section headers, that should be all we need for now. Again, if you really want to like, if there's something you want to do in your document and you don't know how, there are these cheat sheets that are really cool. There's the, we have a cheat sheet here for dplyr. So that's the filter, mutate, select, group by summarize stuff I showed you today. It's a little more comprehensive than what you need to look at, but this will list out what all the functions in the package do, right? If you want to get your head around particular functions. And there are help sheets for RStudio or for R Markdown. There's 2 of them that you could poke around in if you wanted to. Or if you just Google R Markdown cheat sheet, you'll get there too. Okay, so homework for the week. Is going to be some exercises using those Tidyverse functions that we introduced today. So I want you to read chapter 5 of R for Data Science written by Wickham. It's available for free online. So follow that link. It's the data transformation chapter. So I want you to read through this chapter. You're going to use this data called NYC flights that you'll need to install the package for, but you know how to do that now, right? Install.packages, quote, NYC flights 13. And it's going to be this giant data frame that looks at airline data. And you're going to, so this is 330,000 flights, right? So you're going to work with a data frame that's 330,000 rows. And we're going to try and answer some questions with it. And, 330,000 sounds like a big number, but that's a pretty typical size for a real world data set that you'll be working with. So it's going to kind of work you through how to manipulate this data set in various ways. And I want you to read the chapter first and then work through these exercises. 5.2.4. So if we go to 5.2, I want you to do all of these in 5.2.4. So for example, find all flights that had an arrival delay of 2 or more hours. Now, if we look at, let's just kind of take a second to think about what that might involve. I'm going to install the package real quick because I don't think I have it. Not 14, 13. And R saying that doesn't exist. 13 does though. And you can see it's going on the web, downloading the data. All right. NYC flights 13. Okay, so let's think about what that is. The object called. The object is called. It's called flights. Okay. So we're going to say head flights. If we want to get a sense of what's our environment, what's in our environment, we forget what this thing might be named. We have this Explorer tab here, this environment tab. It'll tell us all the things that are loaded into our environment. Flights is not showing up, whatever. It's just called flights. Just remember it's called flights. So the first question is, what's that?
The library is called flights.
The library is called NYC Flights 13, and the object is called flights. So let's take a look at this first question. Had an arrival delay of 2 or more hours. So let's find all the flights that had an arrival delay of 2 or more hours. First, let's look at the data frame and see what we got here. So do we see anything that looks like it might be arrival time or arrival delay? Yeah, right here. And if we want to learn more about this, we can do question flights, and it'll tell us a description of what each of these variables is, which could be really useful, right? Scheduled departure and arrival times, format, hours, hours, minutes, minutes, or hours, minutes, minutes. We can see that these delay variables are in minutes. Negative times represent early. Okay, so that's all we need to know for now. So we want to know something that had an arrival delay of 2 or more hours. So what would we be looking for there? How would we express 2 or more hours in terms of how this variable is measured? 120 or greater, right? Greater than or equal to 120. And what commands could we use to do that? We could use filter, right? Because filter allows us to sort based on values. So what we could do is we could say delayed flights is going to be flights type filter R delay greater than equal to 120. It helps if I type things correctly. As I told you, typos will make your brain explode. That's okay. So now let's look at delayed flights and see what we got. Should be only flights that had substantial arrival delays, right? So we started with 336,000 observations. Once we ran that filter, we were down to 10,000. So this is a quick way to subset a ginormous data frame down based on some criteria that we're interested in. How many flights were delayed more than 2 hours? 10,000, right? How many flew to Houston? I'll just do this one more and then I'll kind of leave the rest to you as you go. Flew to Houston, IAH or HOU. I haven't showed you this in lecture, how to use OR, but he'll walk through in the book chapter how to use the OR command. So there we'll do flights, filter, and where do we see something that would tell us where the flight went to? Destination. Origin is where it took off from, destination is where it landed. we'll say dest equals IAH. And then in R, the vertical bar stands for or dest equals, what's the other Houston airport? HOU, thank you. So now it's going to return me an object where the destination must be equal to either IAH or HOU. So everything that is not IAH or HOU is going to get excluded. Yeah.
Percent symbol function, I forget what it's called.
Pipe.
We're not doing functions together, or is it just like a?
It's just how I write.
Okay.
No, we could easily do the same thing. Pipe just feeds it the object that it's working with. So you can either pipe a data frame into a command, or you could just filter flights. Either way works. So I think that this one will be challenging. I expect this homework to be challenging. I tried to rule out the questions that I felt were too tricky. So I don't think any of these questions are especially tricky, but they are challenging. So I'm going to start a homework 2 channel on the Slack right now. And any questions you run into as you go, please post there. A lot of folks were direct messaging me on Slack, which is fine for questions that you just want to talk to me directly about. But 98% of the time, if you have a question, other people in the class also have a similar question or would benefit from seeing our exchange. So just post everything directly in the homework 2 channel. And that way I can jump in. And I noticed I was really pleased with it over the weekend that a lot of you were answering each other's questions on the Slack too. And that's exactly what we're after. That's exactly what we're after, is I want us to all be kind of learning together. So I will typically respond within a day to a question on Slack, but your peers might jump in there and get there before me. So we'll get that going. Again, this one is going to be challenging. And I'm not looking for perfection. I'm looking for effort, right? I'm looking for you to try and stretch your brain and learn some new coding. And we're basically going to go all the way through group by and summarize. And you're going to do exercises for filter, select, mutate, group by, summarize. And then we'll go from there, okay? Any last questions? And Sophia apologizes. She had a car accident this morning, but she's okay. Bender, but she'll be here next week, hopefully. And we will get the homework solutions are posted now. So if you go to the course website, which is just, it's stickied on the general channel in Slack. So if we go, right. Oh, that's homework 1. Okay. Yeah, so if you go up to the top of the general channel on Slack, there's the course website. If we go to homework assignments, now homework 1 solutions have been posted as an R Markdown. So you can review my solutions relative to what you did for homework 1 there, if you like, and we'll get the homework turned around and graded as soon as we can. Again, I want you to put your best effort into the homework, but I also don't want you to be stressed about grades on homework. Sophia and I will talk about what the standards are going to be, but if you give me a good effort through this semester, you're going to get an A. I'm just going to I can't put it more directly than that. If you put the energy in, you're going to get an A. And the only people I won't give A's to are the people who aren't submitting homeworks or I'm not seeing the work. That's it. So yeah, if you put the work in, you're fine. Okay, cool. So yeah, in office hours, did the timing work for everybody? No. What I think I'm going to do, what about right after class? Does that work for people? So I'm going to change my office hours to just be immediately after class. So we'll go from 12:30 to 2 immediately after class. And if that doesn't work for anybody and you want to talk, just email me and we can set up a separate time to talk. You have class right after. So we can, if you'd like to chat, we can set an appointment for another time and just do a Zoom call. I can be flexible there.
So no more Friday?
No more Friday regularly. I think we'll just do, those can be by appointment. Is that okay?
Yeah.
Okay. Okay, I'm on campus anyway, so we might as well just do it. And it seems like everyone, it's fresh on your brain. Maybe we can talk. Okay. 13.